Alright, so today we continue our journey here with series and certain tests that help us determine whether or not the series converges or diverges. And usually that would be enough to keep us happy. Well, often that would be enough. Here we have something called a direct comparison test, which I like to think about it as this way. My series is bigger than yours. What that means is, suppose that you've got yourself a series that you know, for example, this one is incredibly famous, 1 over n. Everyone knows that's infinite. You can use the integral test, for example. And suppose I've got a series here that's even bigger than that one. So this one, if we already said this one is infinite, well, and this one is bigger than or equal, that forces this one, it must also be infinite, and it forces you to the conclusion that this one must diverge. Okay, it's important that you keep it that way. You got something bigger that's infinite, it has to be infinite. It doesn't work the other way around. Suppose I have something that's infinite and I have something here that's less than or equal to infinity. Well, all bets are off. There are so many things that are less than or equal to infinity. It could be 7, it could be 11, it could be 113, or it could be infinite. So it doesn't help you to bound it the other way. However, this is not helpful. This one, you can conclude something. You could say something like this. If you have something that's, you can bind it by something that's finite, and you have something that's even smaller than or equal to something that's finite, then you know this one has to be finite. Well, not so much. You have to be better than 0. Otherwise, you might go all the way to negative infinity, and you'd have trouble there as well. That's the idea for comparing, direct comparison, when you say, okay, my series is bigger than yours. Well, that doesn't help you unless I know that yours is infinite, then I know mine is infinite as well. Clear? Or the converse would also be true with finite. You want to prove things that are positive and less than finite. That shows that they're finite. But this doesn't help. Alright, talk is cheap. Let's actually do it. That's the main idea. Let's see how we could apply it. Suppose we want to prove that, suppose I want to prove that this series 3 over n, as n goes from 1 to infinity. Suppose I want to know if it diverges or diverges, converges or diverges. Here's what we can do. We start off with some logical stuff. We're going to compare it to the one I just wrote, which is famous. It's called a harmonic. Here we go. So we start off with a simple statement. 1 is obviously smaller than 3. That would force 1 over n to be smaller than 3 over n. Slap some sums on both sides. If you missed that here, first you show that that's always true for sufficiently large n's. In fact, this is true for all positive n's. Slap the sum on both sides, and that would work for 5. There's nothing special about 3. You could play this game with 3, with 5, with pi, with anything that's bigger than 1. You could do it all day long. Anyways, in our particular case, we set out to prove this one. We next note that this one is equal to infinity already. It diverges by the integral test. That's this one right here. So, and this one is even bigger or equal to that one. That forces, you can skip this thing in the middle here, that forces this one to be bigger than or equal to infinity. It forces you into this statement, and then you can conclude, well, it diverges. That's called the direct comparison test. Okay? Come back and we'll do another example like this one. Keep them short and sweet.